Hello, everybody. It's Chris Hopkinson here, Professor and Research Chair in Remote Sensing in the Department of Geography and Environment at the University of Lethbridge in Alberta, Canada. It's a pleasure to be at the Teledyne Optech user group meeting today, and I'm thankful to Malik and Dennis for allowing me to present my work on video. So what I'm going to do now is just share my screen. So there we go. You should be able to see my title screen now. So the first thing I need to do really is acknowledge my many co-authors on this presentation. It's been quite the team effort. Some of my lab members, Celeste Barnes, Maxim Okharenko, Jessica Van Galen, Italo Rodriguez, so all members of our department, and the Institute for Geospatial Inquiry, Instruction and Innovation. Also, James Craig and Hannah Burdett at the University of Waterloo for their support on the Raven modeling. Ryan McDonald also supporting on the modeling side of things. Brandy Newton helping to coordinate a lot of the field work across the Alberta Eastern Slopes and provide other sources of advice. And of course, our friend Malik Singer, who is with some of you today to help us on the Lidar logistics side. So the title of my presentation today is Airborne Lidar Sampling and Imputation to Model Snowwater Equivalent in the Canadian Rockies. And on the right over here, you can see the eastern slopes of the Canadian Rockies, where Alberta borders British Columbia. The black outlines are the headwater subbasins of the Bow Basin, and the blue outlines are the headwater subbasins of the Oldman River Basin. And altogether, there's around about 20,000 squared kilometers in our area of interest, upstream of Calgary and Oldman. Now, you'll see this QR code there. If you can scan that, you will get to a website. And it is an Esri story map, and this was put together by our team, but under the leadership of Jessica Van Galen, who is also doing her master's degree right now in snowpack mapping in the headwaters. And so the story map provides a little bit more information that I'm going to present in my seminar today.
The University of Lethbridge has collaborated with the provincial government and an aviation company from Calgary to get a better handle on snowpack levels. Spring melt from the mountain snowpack has become an increasingly important issue with the continued threat of drought. Chris Hopkinson, a professor with the University of Lethbridge's Geography and Environment Department, says the new method of measuring is called light detection and ranging. He says it gives researchers a much more accurate picture of the snowpack.
This kind of information would be of value in any year because it gives us an absolute estimate of the quantity of snow in the headwaters. The current monitoring that the government of Alberta implements, or any jurisdiction implements, just simply can't give you an absolute estimate. It gives you an index or a proxy for the amount of water that's held in storage in the mountains. This gives us an absolute measure.
Hopkinson is hopeful the operational research will continue in the years ahead. A team of researchers at the University of Lethbridge was recently enlisted by the Alberta government to help with accurately measuring the snowpack in southern Alberta. Researchers were also asked to take a look at the variations from one watershed to another. For 7 months a year, scientists with Alberta Environment and Protected Areas venture into the mountains in the backcountry to measure snow depth and density. U of L researchers were able to utilize data obtained from airborne Lidar, a remote sensing system that can map snow depth for more accuracy. And those involved say with several years of drought, having an accurate measurement is more important than ever.
We have population increases, there's always going to be pressures on our water resources, so there is a need to have more accurate and spatially widespread methods to tell us, to inform us on how much water is in the headwaters. And so I think this kind of remote sensing based research is likely to be something we need to explore moving forwards.
Those involved say that while the Lidar results are comparable to traditional measurements, it can also provide more spatially precise information.
Okay, so a couple of minutes of news clips there maybe give you a bit of a heads up that many people in this part of the world were interested in this research, mostly because we were heading into a drought at the start of the year, and there was quite a bit of concern that maybe we wouldn't have enough snowpack in the headwaters, and we might have to implement some emergency water restrictions. And so that's why the province of Alberta engaged my lab in supporting this program. So a bit of broader context, of course, the Prairie Canada, and of course, across North America in general, agriculture is a multi-billion-dollar industry, not to mention very important for food security and entirely reliant on water, of course, for growing our crops. In Alberta, that means we're reliant on the snowpack in the headwaters because there isn't a lot of snow in the prairies in winter, but there is a lot in the mountains. And so the runoff, as you can see on the map on the right-hand side, drains from the mountains to the east. And we've got many reservoirs and irrigation districts, particularly in the south of Alberta, that are reliant on the spring melt and filling up those reservoirs and then redistributing it out to the crops. So if we don't get much snow, then we have a risk of a drought. And of course, that's what happened at the beginning of this year. We had multiple dry years. And as of January this year, very, very little snow in the headwaters. Now, later on, we did get a bit more, but things didn't look so good in January. And so that's what motivated this project, primarily because we need monitored data to support forecasts through a variety of modeling scenarios and statistical estimates. But those are guided from field data, which are very sparsely collected and maybe not they don't give you a complete picture. And so if you're facing a lean year, you want as good data as you can possibly get. And so the goal of our study was to evaluate a regional snow water equivalent modeling framework, or to test and evaluate that we have been working on this for a few years on and off, but at a much smaller scale. So the idea this year was to map across the important parts of the eastern slopes for irrigation purposes, so for drought mitigation. So essentially, this was to utilize airborne LiDAR for snow depth sampling, and then in this particular iteration of the modeling, to use field-based estimates of snowpack density, and then implement a spatial imputation routine to give us continuous maps of snow depth and water equivalent across the Bow and Oldman basins, and then to integrate all of this into a water forecasting model. So what I'd like to do over the next few slides is illustrate the progress that we've made. This figure on the right illustrates the monitoring locations that are sampled every month during the winter. So November through to May or June, each of these sites is visited by a team of public sector technicians and scientists to extract snow samples, monitor depth, monitor density, and ultimately compute snow water equivalent for each one of those locations. So it's around about 30 sites, give or take, and several hundred individual measurements. So it's quite a bit of data, but it's over a very large area. And so the spacing between those sites can be many, many tens of kilometers that are unsampled. And of course, as I'm sure we all know, snowpack can vary quite considerably over very short distances. So even though we do have measurements of depth, density, snow water equivalent, and reasonably accurate locations, it's still very sparse and essentially only allows a statistical estimate based on historical records that go back over a century in some places. So very good records, very many data points, but spatially not continuous. And this does create some challenges. Now, we have been active in utilizing airborne LiDAR for snowpack research for many years. In fact, myself and my colleague, Mike Sitar, first started to do this in the winter of 98 into 99 in the Rouge River Valley in Toronto, not far from the Teledyne Optech offices. Our very first attempt was unsuccessful. I won't get into why, but that was the early days. But then we tried again in the winter of 2000 to 2001. And that was more successful, and that work was ultimately published in Photogrammetric Engineering and Remote Sensing in 2004. And then again, based on that work, the government of Alberta and the city of Calgary employed my lab to do a similar study over the Elbow watershed, which drains directly into the city of Calgary. And that was also a sampling strategy, similar to the one we're going to look at today, although it was over a much, much smaller area. For this year, we employed two surveys. I'll talk about the details of two in a minute. But the first of which we utilized a state-of-the-art Teledyne Optech Galaxy. One of the reasons being it's optimal for mountain environments, and I think this next slide will illustrate why. The swath track capability, or rather the traditional airborne laser systems with a fixed scan angle, fixed field of view, gives you the kind of skinny and fat swaths in high terrain relief environments, whereas the Galaxy with its swath track allows you to get these parallel swath sampling, and that's what we needed. So I reached out to Malik, and we loaned a Galaxy for our first samples in March. And I'll go through the configuration in a minute, but I think as everybody knows, one of the primary uses of LiDAR, of course, is to generate digital elevation models and various derivatives of that, such as aspect, slope, and of course with the full point cloud information above the ground surface, we can map canopy attributes as well, and even more derivatives. It isn't my intent to get through or get deeply into what LiDAR can do right now. My assumption is that you have some general knowledge. But of course, if we're generating a digital elevation model over a snowpack, then that snow surface is going to be elevated over the terrain a little bit, and therefore we can simply subtract the terrain model from the snow model, and we should be able to get something close to depth. Now, our first missions, of course, we were actually colleague Alex from Teledyne actually flew these surveys for us, and so you can see some of the footage that he captured for us. Winter's not necessarily the best time for flying over the mountains. You've got shorter days, very often low clouds, and as this image illustrates, the clouds themselves are hanging around at mountaintop or even lower. So that's of course one of the challenges for flying in these environments. Another one, of course, is the ground conditions. It may even be may not be apparent to the air crew what's happening at ground level, but this illustrates that you can get quite a lot of wind, and that wind can be blowing the snow around. And if that is happening, well, then that could impact your data processing, and we'll look at that in a little bit later. Now, in my lab, we actually have a Titan, so it's a few years older, does not have swath track, so we have those kind of skinny and fat swaths over the high relief areas in the mountains, but we've been able to make do with that. So what we did was we flew the Galaxy for our first mission in March, and then we flew the Titan for our next mission in April. Now, there are a number of reasons for the rationale, but obviously the Galaxy for swath track, but Titan has 3 wavelengths or 3 channels, 532 or green, 1064 near infrared, and 1550 shortwave infrared. So with those 3 wavelengths, of course, we can do some interesting things, and the idea was that we would see what we could do with the snowpack. And I'll get into that in a couple of slides, but first of all, as you noted with the Galaxy, we were flying at mountaintop level because of clouds. We can't be flying above the clouds, of course. With the Titan, even if we've got perfectly clear skies, we're also flying at mountaintop because we have more of a range constraint. We can capture data up to about 2,000 meters in the infrared channels, but the green struggles in those ranges. So we have to fly a little bit lower. So you want to make sure you're looking out of the window when you're on these missions in the mountains. Okay, so why the Titan? Well, as I mentioned, we've got the 3 channels, and I think many of you have probably seen a figure like this before, where you can see how each one of those channels interacts with the various land cover spectral response. So the examples there are water, vegetation, and soil, but of course there's many other different types of surfaces that are going to behave differently. And we're interested in snow, and I'm not going to provide any spectral information of snow just yet, but we'll have a look at that much later on. But anyway, just a reminder, we can get terrain, we get canopy information, but with the Titan, of course, we can generate some interesting intensity images. And so you can see in the bottom right there an intensity composite, which looks something like a photograph. Now, if we look at some intensity data from each one of the channels, so shortwave infrared on the left, near infrared in the middle, green on the right, you can see they're just like black and white photographs, each illustrating different features in the landscape, just like optical remote sensing data. So that's one of the real values of the Titan. Now, if we look at this in a little bit more detail, here we can see a time series over a mountainous environment. Incidentally, this is the Cameron Valley and Waterton Lakes National Park. This is 1 year after a wildfire, year 2, year 3, year 4, year 5. And if you look really closely, you can see that landscape is greening up. And that's because we're able to generate a false color RGB composite from each one of those 3 channels. Now, of course, we can also develop normalized indices. Now, in a snow context, the active normalized difference snow index is very useful. So green minus shortwave infrared, green plus shortwave infrared. So the ratio of those can be useful in giving us snow cover. I'll illustrate that in a minute. But of course, we also have pseudo NDVI or active NDVI and active normalized burn ratio. So these are more familiar ratios that utilize these channels. And yeah, we can pull all that information out with the Titan, and that's one of the things we've spent quite a lot of time doing in our lab. Very useful. Here's one of those composites over the Wapta ice fields, which is also in our study area, the top end of the Bow Valley. And here you can see the snow covering the ice fields here, really obvious coming out in the blue color gun on the composite. And even though you can't really see it in this imagery very well, maybe you can kind of get a hint of it here. These dark areas are ice, and then these lighter blue areas are snowpack. And if you imagine going all the way from ice at about 90% the density of water, all the way up to fresh, dry snowpack, maybe 10 to 20%, you've got quite a range of densities. And one of our ideas that we wanted to test was whether or not we could capture that density range in the intensity signals. So we'll look at that at the end, but this image maybe gives you some hint as to why we might think that could work. Now, as I've noted, we have done quite a lot of LiDAR-based snowpack research going all the way back to 99. But more recently, we've been doing temporal data collections over one of our headwater basins, which is fairly well instrumented. And so students of mine have been looking at a number of the snowpack controls at a range of spatial and temporal scales. So this study is not about proving that LiDAR can map snow depth. Of course, it can. We've shown that, and many others in the US and Europe have also shown that, particularly the Tom Painter's group in the US have done very well in commercializing the technology, in fact. So I'd say it's a very well proven technology now. However, going beyond depth into density and snow water equivalent, yes, progress on that has also been made. Again, the folks in the US have made great progress in integrating LiDAR and other optical techniques. What we're looking at here, though, is a much larger area. You can see here watersheds. We've got lots and lots of data at the watershed scale, so a little over 100 or a couple of 100 square kilometers. That's no problem to fly. But if your area of interest is on the order of 20,000 square kilometers, we're clearly not going to be flying that in 1 or 2 survey flights. But if we are limited in time, as we usually are in the winter, then we need a different strategy. And so that's really what this study is about devising a strategy to sample over that much larger area. Now, in terms of densities, we've done a little bit of work on mapping and modeling densities as well, and but that work is in progress, so I won't discuss that here. For this study, we're just going to rely on sample data. And of course, the government of Alberta at their 30 or so sites in our study area have many decades of archive data. And so what we know is that the field estimates of density, when you average them at a particular site, they tend to vary between 20 and 50%, or more normally between 30 and 40%. There's a range there that's fairly common. And towards the end of winter, we're somewhere in the, just above 30% is about normal. Now, of course, it does vary as the snowpack is melting out. It can vary. It can vary with elevation and with canopy cover. So there are a number of systematic space and time controls on density as well. We're not going to look at those in this study. They're being looked at in another one. And so for the purpose of this study, all we have done is taken the field-based observations of density from those 30 or so sample sites, and then we've averaged them for the start of March and the start of April data collections, and we've just applied them. So it's a rather simplistic approach. We know we could do better than that, and that is our intent moving forwards. But for the illustration today, we're just using average field density. And of course, when we apply that to the depth, that gives us our goal of snow water equivalent. And so you can see illustrations of what the density and SWE maps might look like at a watershed scale. But of course, we're scaling up. So we did our first regional assessments last winter. It was very experimental. We were coordinating with Alberta Environment, and we were trying to coordinate the field crews and the air crew, and we really worked out that it wasn't as easy as we had hoped to coordinate all of those activities. And over an even larger area last year. And so we this year we modified our plans a little bit, and you can see the two main mission areas, green being the Bow and green to the north, primarily the Bow Basin, yellow to the south, primarily the Oldman Basin. And then there were two sets of missions in March and April. The March missions all occurred on 2 days, the 6th and the 7th. The April missions were also on 2 days, the 1st and the 10th, but as you can tell, they were separated further apart. And we'll talk about some of the time separations later on, because they created some challenges with the analysis. This is the Galaxy mission, and you can probably make out on the right here, all of these swaths are very, very rectangular, very nice and uniform transects. The Galaxy lived up to its promises there, but due to weather constraints, we were not able to fly the most southerly part of the Oldman, which was a real shame, but we did get very good coverage in the Bow and for the northern part of the Oldman, which hydrologically is actually more important, because maybe you can just see here, there's one of our major irrigation reservoirs in the headwaters of the Oldman is just downstream of this part of the Oldman. So if we could sample these parts, then we get almost all of the SWE that contributes to that reservoir. So that was very useful. Shame we didn't get everything, but we got most everything that was critically important. And here you can see some members of the team, Jorge, Maxim, and our pilot from Aries Aviation. So here's a walkthrough of the Titan. So now we're on the April mission. If you look closely at these swaths, they're a little bit more skinny and wider, and it's a little bit more variable in terms of their width and also the sample point densities, as we expect with the Titan. This time around, though, we got very good sampling in the Oldman, but not so good in the north end of the Bow. Again, weather, just very challenging to get the ideal conditions. And so eventually you wait and wait and wait, and then you run out of time. So it is what it is. So as an overall summary then, we flew 28 hours, which included 2 calibrations, 5 actual survey or mission flights, 2 different sensors, the Galaxy for March, the Titan for April, nominally 1 kilometer wide transects. Now, importantly for us was the experimental design for validation. So the first component of validation was where the flight lines overlapped. We wanted to make sure that our Lidar depth or snow depth maps were consistent from survey to survey. So we had 85 flight line overlaps for that. What we found was that there was a 12 centimeter RMSE, nominally a mean magnitude offset, so not an average offset, but a mean magnitude of plus or minus 6 centimeters. So our mean deviation was averaged around about 6 centimeters with a 12 centimeter RMSE. But as we had hoped and expected, there was a very high depth covariance of 0.7 or 70% of the variance explained. So overall, quite satisfactory. We think we could do better than that, but for the first major assessment, we're quite happy with that. As I mentioned earlier, of course, ground conditions can be a pain if it's windy. This is rather extreme, and so this is something that you can see up in the Alpine, up in the Oldman, on one of the ski hills that we work at. It's not always that bad, not always that obvious. However, if you're collecting LiDAR data over this, this is what you're going to see. You're going to see lots of point clouds up in the air, lots of atmospherics, and they're going to need to be filtered out. So we had a fairly rigorous quality control routine. Only so much of it could be automated. Of course, we do automate as much as we can, but nonetheless, when the data is like this, you've got to do quite a bit of manual QC as well. So we developed some routines for that, and then ultimately did a lot of comparisons and checks for data accuracy. Following the data cleaning, we removed a little over 30% of all of the ground coverage because it was either obstructed, occluded, or too noisy. So that's a data loss. And then we aggregated our depths up to 30 meters, and you'll see why in a minute. That allowed our depth imputation process where we would then add density, and then we could calculate snow water equivalent. So the first element of validation after the flight line to flight line comparison was to compare the LiDAR snow depth maps with the field data. And now the field data were variously sampled, either with survey grade GNSS at the point. That would be the best. And in those cases, we know we're within a few centimeters of co-location between the LiDAR and the field data. But more often than not, we would have two survey grade GNSS at either end of a transect. And then we would systematically capture every few meters along the transect. And then in the worst case scenario, we would have two handheld GPS coordinates either end of a transect, and then we do the same thing. So nominally, we're within a meter or two in terms of co-location accuracy between field and LiDAR, but it could be up to 5 meters or more off. So bear that in mind. But nonetheless, we're quite happy with the overall validation results. If you look overall from all of our data, so almost 200 data points, the field results are telling us our average depth was 1.08 meters. LiDAR was telling us it was 1.04. Some more statistics there. But then from each of the different campaigns, the airborne LiDAR campaigns, you can see the comparisons with field data there. But it's very, very important to note that they weren't all coincident in time. So for this March campaign, the LiDAR data were up to 6 days after the field data. And then April 1, 4.5 days, and then April 10th, 5 days. So if we've got that kind of a separation, of course, the snowpack could be growing if there is snowfall, or it could be compressing if there's melt going on. So you have to bear that in mind. There is some of the error and uncertainty will be due to that temporal gap. Now to the imputation. So this is where we map the snowpack over a very large area. So we're implementing random forest imputation. We did this in 2 ways. First, we used Google Earth Engine because it's quick and efficient, and lots of data layers are easily accessible that way. And then we also implemented in ArcGIS Pro because we could do things in a little bit more heads-up, iterative way that way. We have no preference. Either environment works. Maybe a few more artifacts in Google Earth Engine, but nonetheless, either works and can generate maps of snow depth. So random forest integrated the gap fraction from LiDAR. I'm not going to get into how that was created. That's another paper, another study. But anyway, we have gap fraction. We have various terrain indices and elevation, of course, from ASTA GDAM, 30 meters. And we have many Landsat derivatives also at 30 meters. So all of those have gone into the imputation and produced a snow depth map. And here you can see the product. So here's the extent of our map. It actually goes beyond the real area of interest, which are the drainage basins. And I guess the first thing is from a training point of view, we were consistently getting R-squareds of above 0.94. But then when we look at the out-of-bag accuracy or the validation, so the data that are kind of withheld from the training, we're still getting over 90%. So we were quite happy with that. Now that's relative to the LiDAR 30-meter transects. So the training and validation results from the imputation were quite acceptable. But then, of course, we apply the field estimated density to compute SWE, and then we can compare the 30-meter gridded SWE with the nested field estimates of SWE. Now here we see a bit of a discrepancy, very high covariance, but for March, we had a linear regression or slope of 0.76, and in April, 0.79. So we're systematically underestimating the SWE when we apply the field-based density. Of course, we could calibrate it, right? We have observation, we could calibrate it up. We didn't do that in this particular case, not for the validation. We are working on density in other ways. But for now, we're just presenting this as it is, just using the field estimates, and that's what we get. Now, of course, there are some scaling problems. We've got in situ measurements at a point that are being nested and aggregated and then applied to a 30-meter grid. And that 30-meter grid, of course, is smoothing out a lot of variation. We are not applying any canopy or elevation-based adjustments, which could move those estimates up. And critically, let's also consider there is this temporal discrepancy. Now, because we don't really know what the source of the offset is, we're not exactly sure which should be the best source of correction. But it could be, theoretically, that the temporal discrepancy is enough to justify or result in this 20 to 25% offset. So it is what it is. We're going to report it as it is right now. And one of our areas of active research right now is improving that density estimate. So I'm not going to go deeper into that right now. But the element of temporal discrepancy is important, so I just want to stress this and reiterate it. If we look at the plot on the bottom left here we can see the snow pillow and the snow water equivalent as it tracks from October of 23 into the spring of 2024. So the blue line represents this year, and these three lines, the yellow, green, and blue, represent the three LIDAR missions. So March 6th and 7th, April 1st, and April 10th. And so you can see that the SWE is tracking up during that time, but it also just starts to track down on April 10th. So it's kind of accumulating all the way up, and then on April 10th, things have already started to melt. So what we actually saw in the field was that the snowpack was in fact melting out in the valley. But meanwhile, there was still accumulation of high. So in the April data collections from the 1st to the 10th, we would see high elevation accumulation, but low elevation melt. Meanwhile, from March 6th and 7th through to April 1st, it was just net overall accumulation. And I think you can maybe understand that if you look at the temperature tracks for many of the sites throughout our study area. It was generally pretty cold between March to April. A few days above zero, but not a lot. And then between the last two surveys in April, it was predominantly above zero, so it was quite warm. And then if we look at the precipitation, lots of precip from March to April. And then even in the last or in the first few days of April, there was also quite a bit of precipitation. So overall, quite a bit of snow accumulation between both time periods. But in the latter one, we also had melt. So it's kind of confusing it when you're trying to compare field data and LIDAR data collected at different times. Very, very dynamic environment. Nonetheless, if we take the data as being representative of, first of all, March and then April, if we take those as our two time periods of interest, we can aggregate the depth, density, and snow water equivalent at the drainage basin scale or at the sub-basin scale, and then we can relate that to historical runoff or hydrograph data. So we have done that, and we've created a useful metric of the basin snow water equivalent over the historical summertime yields or the historical annual yields. And so then we get these statistical representations here. Also, we can relate the difference from March to April to precipitation records. And so here you can see the increase in basin SWE for each one of these basins. So from March to April, so you can see it's consistently increasing. And that's as we expect because there was continual snowfall during March and it was generally still quite cold. So that's exactly what we expect. And of course, we can relate that to precipitation records. And then finally, what we can do now is, because we have a spatially explicit estimate of a drainage basin SWE, now we can implement these in hydrological models. So my colleagues at the University of Waterloo, Hannah Burdett and James Craig, took our SWE data for the Oldman and applied it to an existing model setup of the Raven that they already had. And so these are the basins, or the HRUs, and there's the reservoir that I mentioned earlier. And so they've been modeling the runoff draining into this reservoir. And the way they do it is they'll use the gridded weather data to build snowpack and add precipitation and then route it through the basin. This simulation was initiated in 1998, and then using the meteorological data was ran all the way through to March 6th, 2024, the day before we had our first data. What Hannah and James did is they took our LiDAR data and then inserted it into their routine so that they could essentially recalibrate the SWE for the basin. And so using that update meant that they could re-optimize the March condition. So you can see, after applying the LiDAR, they've re-optimized the model for SWE in March. So you can see it's much larger than it was originally. And then that can then be ran from March through to April. And then this April product can be validated against our LiDAR product. And so this is a kind of a new implementation within this modeling environment, utilizing this data framework that we've created from the sampling and imputation. So this is also a work in progress and holds a lot of promise. Now, finally, I mentioned earlier that we were going to look at density. So again, this is a work in progress. We haven't got too far with that, but there's enough literature out there that proves that various snowpack properties do vary in terms of their optical reflectance. And so here we can see that various structural metrics, which correlate very well with density. So here, 10 to 25% of water equivalents, 20 to 40%, and 35 to 50% are represented by these three different colors. And then here you can see the spectral response in the near infrared and shortwave infrared. So quite a bit of difference. Obviously, the shortwave infrared is generally less reflective than near infrared, so that's already well known. But the interesting thing is whether the ratios of those two wavelengths are going to change as the density changes. And then, of course, from dry to wet snow, we also see some considerable differences across the spectra. So what we did was we took the field density, and then we compared the field densities at the site level with the individual channels, and then with the normalized ratios, and then a variety of indices of all three. And the one I'm going to show you is NDSI multiplied by NBR. So first of all, just the straight out regressions. Noisy, as I think we would expect. So here we've got the individual channels versus density. So green, near infrared. The best of the three was shortwave infrared. Maybe not surprising, but R squared of 0.42, so not very strong, but also quite noisy data, so quite encouraging. Here's our channel-to-channel regressions. Green and near infrared, quite highly correlated, not highly surprising. Green and near infrared, near infrared and SWIR, and green and SWIR are less co-varying. And if we look at the ratios, the only one that really shows much promise is the normalized difference snow index and snow density with an R squared of 0.34. Maybe not a lot of surprise there. NDSI, it's a snow index, and seems to co-vary with density at least to some degree. So SWIR shows a high regression, 0.42, NDSI, a low one, 0.34. But then if we consider the data gaps, -8 to -2 days of data gap between the field and LiDAR bow, and then -5 to +1 with the field to LiDAR for the Oldman. So if we take the three channel index, which is NDSI multiplied by NBR, so if you think about it, the shortwave infrared is the one that's been most utilized because it's embedded into both of those indices, but then they're ratioed. One is ratioed against green, another is ratioed against near infrared, and then we multiply them. So we've got all three wavelengths in there. And then another thing I've done here is I've removed those data sets that are most distal in time. because after a little bit more digging, what we discovered was that some of the low elevation data, when we get to April 10th, almost certainly melted out, or within the 30-meter pixel that we were looking at, they were probably quite patchy, not very reliable. So by removing the obviously bad data, this is what we get. N of 36, although each one of those points is represented by up to 5 individual samples. And each 30-meter grid cell is represented by potentially hundreds of Lidar return samples. So that's why there's quite a bit of noise in there. But now we're up at R squared of 0.6. So this is really encouraging, and I think we can do better than that. So still, time is one of our problems, and I hope this illustrates it here. So if we just look at this bottom graph here, this is, we have two SR50 snow depth gauges at 2 valley locations in south of the Oldman. So Cameron is in Waterton, right in the south. And then this one is Castle, which is kind of in the middle part of the Oldman headwaters. And so what we see is that from our first field sampling in the south, where we hit 4 sites, or the Alberta environment hit 4 sites on the same day, March 27th, the overall mean density was 31%. Now, the last field data collection at a site in the Oldman showed a mean of 36%. Now, the variance is really high. I mean, there might not be a statistically significant difference between this density and this density, but this is nonetheless the mean. And the Lidar was in between the two. So the Lidar here is April 1st. This field sampling is 1 day later, and this field sampling is 5 days previous. And here we see the snow depth for the SR50. So after the first set of samples, we have some on the order of 12 centimeters of depth increase, and that equated to 15 millimeters of additional water into these areas. And so the Snowpack got about 30% deeper as a result. Now, after the Lidar, you can see the Snowpack is rapidly melting, and that was the case on the first. April 1st was a warm day. We see rapid melt, and then by the time of the sampling in the field, it's melting again, because we're in the second warm day, and so we were losing Snowpack quite quickly at that point in these locations. And so now we're up at a density of 36. So we see an increase in density. And so all of those observed changes in the south are consistent with a 5% density increase. Well, the take-home message is that the Lidar sampling plus imputation has enabled a large area SWE map or model to be developed. When you consider the scaling and the method of sampling and the integration and the temporal challenges, what we have found is that we've produced a slight underestimate of the SWE. However, in an operational context, that could easily be calibrated out. These data can support hydrological modeling. We've demonstrated that you can optimize a hydrological model and therefore use it for forecasting. And the multispectral Lidar intensity does show promise for density modeling, or at least as an additional source of information for density modeling. We're also using canopy cover, elevation, and other terrain derivatives for that. So the next steps are to complete the full water balance scenarios through the hydrological models for 23 and 24. So that's ongoing. And then we really do hope to refine and repeat this for next season. So I'm going to wrap things up here. I'm going to thank our various funders, so Government of Alberta, Alberta Innovates, Optech, of course, for their support, and many, many other partners and supporters. And yeah, thanks for your time. Anyone has any questions, please feel free to drop me a line by email. Thanks a lot. Bye for now.